Hi everyone, very nice to be here, and yeah, I work just around the corner, like that corner particularly. Yeah, my name is Alex. I'm working for a company called Instana. We're located basically right here, so in this glass Kasten, right behind you. And I'm gonna talk about like unconventional usage of Cassandra, because we're doing lots of streaming. We decided not to use Spark, and just because it's videotaped, I can't really say why, because I don't want to be on the record. And the same thing, like that was also the reason why I didn't comment on the InfluxDB stuff, so we can do it off record. I have some experience with time series, and I had some research project of myself, Continuum, which was actually the time series database. And I did like lots of analysis and comparison of the existing time series tools and the aggregation capabilities of them. And yeah, we can just chat about it if you have an interest. So yeah, I work for Instana, and we do application performance management, which is an interesting subject, and you get to work with the sensoric data gathered from across the clusters of machines. You get a lot of data every second, and you have to process it as fast as you can. And this sets a lot of challenges for you as a developer, because you cannot rely on the things like batches anymore, and you have to push the data through your pipelines as fast as you can. And well, you kind of have to throttle down if you cannot process things anymore. You have to scale, you have to partition lots of things. And one of the reasons how this talk came out was us having to do not only like streaming of the data, but also implementing the pipelines which were getting the chunks of data and trying to aggregate them for like kind of as fast as we can customer queries for our data analysts who are, well, crunching the data to make our customer experience better. And we're using Cassandra, and we monitor, like one of the sensors that we have is of course Cassandra sensor, and we monitor, like self-monitor our Cassandra clusters. And this is kind of like what dashboard or our Cassandra dashboard looks like. And if you're interested, I can show more things and tell more about Instana, but probably that's not going to be the point of the talk. And the first challenge of that we were facing is that, and something that sets us apart from the competition, is that when you deal with the sensoric data, you have to be very precise. And you can take a look at these two graphs, and the bottom one and the top one are representing essentially the same exact data, although the bottom one is rolled up. So basically someone who was writing the aggregation for you, so like one of our competition mainly, they've aggregated the chunks of data over the minute or over 5 minutes, and like therefore you always see the flat line. Although if you take a look at the more detailed data, for instance on a second resolution, which has already been a buzzword today, you see the completely different picture. Therefore, whenever you're dealing with the sensoric data, it's very important to be as precise as you can. The second thing which we're trying to do differently from whatever else is existing on the market is we're trying to keep the semantics of the data. For instance, we're not treating the CPU data exactly on the same thresholds like standard deviations, but for instance, for whatever we're doing for TCP activity. So we're treating every piece of data that we get absolutely differently. We use different algorithms for different things, and it yields much better results. So you have to treat your data in the way it wants to be treated, kind of. And the last thing is, of course, the anomaly detection, which is also a big buzzword. Probably the talk is going to be less about it, because I think I'm going to concentrate more on the Stream Fusion part of the talk. Although the second part of the talk that I've given on the Cassandra Summit was also including some anomaly detection examples and clustering and stuff. And if you have anyone read The Little Prince? So if you know that, then you can see exactly what is happening. So you can see the elephants being swallowed by the snake. So the anomaly is kind of built into the brain of the person. Whenever you, for instance, wake up in the morning and you reach to your coffee machine and it's not there, you're gonna notice it immediately. So people are built to detect the anomalies. And that's a challenging project to actually make the machine understand the anomaly exactly in the same way the person does, but it's also doable. So the agenda is going to be how to do the ad hoc queries mainly on the order data. I'm going to talk about something which is called time series, although you can apply the same exact principles to anything that has monotonically incremented key, or you can simulate the monotonically incremented key by, well, doing pretty much sorting on your data. And I'm going to talk about the fast aggregations, how to partition your data in the way to perform the queries in a very performant manner. Unfortunately, because of the time constraints, I have to leave out the part about the machine learning, but we can chat about it after the talk. The first part is how to make your queries parallel. And because we didn't go with the traditional approach, so we didn't use Spark, we had to build like many things on our own. And once again, many examples or many code examples which I'm going to be showing are going to be the Haskell code, because they've been taking out the time series database I've written as a research project. Although the same exact principles apply to the Cassandra too, and I've recently open sourced the project which is called Fusion, which implements exactly the same things, although for Cassandra it's pretty early stage, although it's getting mature, and we're using it already for some things in-house. Therefore, we hope it's going to grow. So parallel queries. In order to make the parallel queries on your time series data, you can take your timestamps that you probably previously already had and add some sequence ID to it. The reason to have the sequence ID, or there are multiple reasons to have the sequence ID. One of them is, well, once again, the buzzword that's already been named today is idempotence. So you know that whenever something has a certain sequence ID and you have already seen it, then probably you should override the old data point. So it's essentially the same piece of data. The second reason to have it is in order to be able to partition your data in some chunks. So you can also use the sequencing in order to ensure the sub-second or sub-resolution order. For instance, you have the timestamps down to 1 millisecond, which is, well, the standard Unix timestamp, although you want to ensure that you have a sub-millisecond order, and you can of course use something like nanoseconds for that, although you can also use the sequence IDs, because if the nanosecond precision is not important for you but only the order matters, then it's going to save you. And it ensures idempotence, and you can snapshot the data whenever your counter overflows. For instance, whenever you've done 1,000 writes, you can snapshot the timestamp that's been written and write it into the different table. And you basically, in order to parallelize your data, you create so-called range tables. Reason to have the range tables is in order to have the chunks of data that are going to be processed in parallel equal. So you will always end up having equal size chunks, which is a very nice feature of the data, because all your queries will run approximately with the same performance, and you won't be slowed down by the largest chunk of the data. So that has helped us a lot. The range table would look pretty much like that. So you have the timestamps which are coming into, writes that are coming into your database. For instance, timestamp 1, timestamp 3, 1, 2, 3, and then 4, and you write this 4, the timestamp number 4, into your range table. Then you wait until blah 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 8, and you write this timestamp into the database. And after that, whenever you're generating the query, you kind of like partition your data, so all your timestamps, into the chunks. For instance, whenever you do the full table scan, you just take the very first timestamp, so 0 basically, and you go from 0 to timestamp 4. The second partition would be timestamp 4 to timestamp 8, the third one 8 to 12, and then, well, the 13 is going to be long. So that's going to be the full table scan. The open range query would start somewhere in between the timestamp 4 and 8, so you're going to start over here, and you're going to take these 3 chunks and process them in parallel. And the between range is, of course, whenever you start not in the very beginning, but somewhere here, and then you take these 3 chunks and you start processing them in parallel. And the second step, whenever you have the partition data, is the large question is, how do I combine the data? And in order to well, combine your data in a very sensible way, you can use, well, something that people have invented many years ago, which is called algebra, which is actually an awesome thing, which I recently learned about. And there is a really nice paper which is called From Lists to Streams to Nothing at All, and it's about the stream fusion. And it's a very interesting concept of how to combine your operation in, or sets of your operations into, well, some higher order operation that is performing or ticking pretty much with everything, a single thing that is coming, like that is being read from the database. So you can use that concept of stream fusion in order to do rich ad hoc queries, and let's dive into it. So what is stream fusion? Whenever you have a 3-step operation, that one is pretty lame because you have map and then filter and then reduce. Usually people do filter before map, which has been pointed out. Although, just for the sakes of it, let's stay with that example. So you take these 3 steps and convert it to the single operation, which is called like map filter reduce, so without spaces, right? So it's like one word, one operation. And the way it's going to be represented, this is some Haskell code, but I think that's also a very concise way to describe the way the stream fusion is working. So what is basically happening, on each step, you can say that you are in one of the 3 states. The first state is you could be yielding. For instance, whenever you're reading the data from the database, whenever there are more data points to read from the database, you're yielding. So you yield at every single read. The second one is going to be skip. For instance, whenever you're filtering data and you want to skip one of the points and you want to notify the, for instance, the reduce operation that, well, I have filtered one of the things, you do the skip. You say, okay, we skip that one, and the third one is done. So for instance, whenever you're reading from the database and you've reached the very end, you say that, okay, we're done, we can return the result already. And the stream would be something that takes the current cursor, returns the step, and the pointer to the next record that could be read. So the stream beginning would be, of course, just reading data from the database. So you take an iterator, and, well, Spark Connector has also, well, more sophisticated iterator, which is called like prefetching iterator. If you like, you can take a closer look at it. So basically what it does, it fetches more data asynchronously while you keep processing the data that is running into well, your iteration. So basically you yield on every step until you pretty much can you reach the end of the database, so you exhaust the cursor. And the next one would be the map operation. So map is basically taking the stream of A and a function from A to B and yielding the stream of B. And as you see that whenever the higher order function, for instance, the iterator from the database says it's done, the map agrees. It says, okay, it's done. Whenever the filter operation, which is standing before the map, saying skip the item, the map agrees with it and says, okay, we skip it. And whenever we're yielding, we take the data point, which has been yielded, and we apply the function, so that function from A to B, to the current cursor, and we pass the cursor to the next record further. So the filter would do something a little bit different. So the skip and done are essentially the same pretty much for all the operations except, well, the well, the specific ones, let's say. So the yield for the filter would only yield whenever your predicate from A to Boolean is going to be the true. So that's kind of a straightforward thing. And the default is going to reduce the whole stream of your data to some accumulator. And the trick, or whatever your, oh, that was the wrong mouse button. The trick, whenever you're done with the processing, remember that we were processing the streams or the chunks of the data in parallel manner. So we've got like 5 chunks of data which are possibly being processed not only in parallel on one machine, but in parallel on gazillion of machines, or like let's say 10 for now. So you get the well, you know, you need to scale, but you can't get to the gazillion with monoids anyways. So what you basically say that whenever you have an accumulator, you want this accumulator to be a monoid. Monoid is a very interesting data structure or very interesting algebra which pretty much has 2 properties. First is called empty. So basically, if you have a body of integers, the empty would be, or natural numbers, the empty would be 0. And append would be a concatenations of the 2 integers. It would be, for instance, plus. So the append for natural numbers could be possibly the sum of them. If you have a list, for instance, which is also a monoid, the empty list would be empty, so the initialization of your monoid, and append operation would be the list concatenation. So good for that. So far, what we have gotten is we have processed the data, so we could like write relatively rich queries on each part of the database. For instance, we have a Mesos cluster, and we process chunks on the workers. And whenever the worker is done, it's sitting with a monoid. These monoids are being passed further to the coordinator node, which is gathering all the monoids and then, well, using the algebra, so it just appends them together. So we just combine them. And you know that whatever the monoid you implement, like whatever the thing you're processing, if you fulfill the properties of the monoid, your result is going to be correct, which is probably the most important thing in the data science and computation. And whenever you have concatenated your monoids together, you may possibly want to convert them into some entity which is going to represent the result. So let's take a simple example. You have the time series data with some sensoric data, and you would like to get the count of all the things. So the monoid for the count would be initialized with a 0. And so whenever you have, well, you start counting things, you start with a 0, and you start processing things on your many nodes, and on each and every data point that your iterator is getting, you're going to increment the 0 and eventually yield the monoid of count with like 155, which is going to be the result of the computation of one node. So the second node is yielding some other result, and in order to combine them together, we, well, basically put them back into the monoid of count and summarize them. So we take a sum of the 2 things. And in order to yield an aggregate, so we say that, okay, here is very straightforward. So the aggregate of the count is going to be an integer. Well, basically because we have concatenated the integers together, and then we say that, okay, that's pretty much our result, but we just need to unpack it from the count. I think, oh shoot, I think I've left out one better example. Let's take the stream of also integers, and we would like to aggregate the average of them. In order to aggregate the average, you could, no, I don't think I can pull that out. Let's just calculate the median. Okay, in order to calculate the median, you would have to, take all the data which is sitting on your nodes. The aggregator would, or the coordinator node would receive the arrays of the sorted chunks of the data from the nodes, from the worker nodes. It's going to concatenate them together into one big array of the sorted, well, integers, and in order to find the median, you basically take the middle of the array or of the concatenated array. In this particular example, you have, well, the monoid of a list. You concatenate them by, well, list concatenation with merge sort, and you just find the middle in the aggregation in order to return the final result. I think I'm gonna skip the rest of the presentation because, well, that one is kind of, it goes very deep into the machine learning stuff, and I think I'm gonna just try to unpack. I'm sorry about that. I think I'm just gonna unpack another presentation. Yeah, I do have a mean. I thought I didn't have it, but I do. So someone who had seen the that slide was tweeting that having 18 lines of Java code is actually okay, but 8 lines of Haskell is a little bit too much. But I hope it's going to do. So the interesting stuff, right? Yeah, what I've been trying to say. Whenever we have we'd like to calculate the mean, we just say that, okay, we initialize our monoid with the empty array, and on each and every node we aggregate or gather the arrays of the data, and we concatenate them, well, with a basically list concatenation. And in order to aggregate the actual mean, whenever we have an array of the data, which we just calculate the sum of the whole array, and we divide it by the length of the array. So that's pretty much it. Yeah, that one is more the talk about the continuum itself. So my point, I was just trying to keep it very short and concise in order to avoid information overload, because it's first of all, the subject is a little tricky, and the second of all, it's not applicable for everyone immediately, therefore, and it's also very or roughly theoretical. Therefore, my point was just to demonstrate the possibility of running the queries in parallel or on many nodes, aggregating the result on a single node, combining them into the final result, and returning the result to user. So that would be the way it's done. And the implementation, the Java implementation that we've been recently working on, it's called Fusion. It's also the project on GitHub. So it's called Fusion. It's under my GitHub handle, and yeah, you can take a look at the examples, like how exactly the stream fusion could be implemented and could be done. Because Java doesn't have well, as many pattern matching possibilities as Haskell, I ended up actually implementing something that looks more like closure transducers, like which are basically the nested lambdas. But essentially the idea remains the same. So in order to summarize it, you take your data, you partition it in chunks, you process each chunk in parallel, you combine the chunks and return the final result. That's it. Yes, please.
So why shouldn't I use Spark?
I won't say anything in front of the camera.
We switch off the camera.
I think I'm also bound, you know, like there is, no, Spark is awesome. The reason we didn't use Spark is for performance reasons, or we are very performance bound and we have to deliver certain guarantees to our users. We have SLAs, and we couldn't meet them with Spark. Same reason with the Storm, basically. We just had to, well, first of all, instead of Spark, we used a totally different set of technology. Actually, that one was a side project of us, which was done mostly for the data science team, which is working with the data of the customers in order to query the data and run the aggregates across the larger data sets. What we use instead of Spark is basically Kafka together with the Reactor or not even reactor, but reactor extensions which was reactor pipes, which is a totally different talk. So we do lots of stream processing, but stream fusion is more, I would say, for aggregation jobs rather than for stream processing. Yeah, but yeah, I'll probably want to pack it. Yes, please?
So when you distribute this minoid, this kind of recursive function, and you distribute it on a bunch of nodes,
yes.
you get the results asynchronously back, so you can basically stream the results as it's working, or does it have to wait for completion of all nodes? What happens if a node drops?
Yeah, that's a big advantage of having, well, monoids. Well, first of all, if the node drops, we just restart the job. So that's as simple as that. But the advantage of using the monoids is, of course, that every single result it could be concatenated asynchronously. So whenever the first node responds, we just keep the result. Whenever the second node responds, we concatenate the result with the second one. And then you theoretically could actually yield an intermediate result if the computation is not expansive, and yield the intermediate result and even show it to your user. If you want to wait for an entire corpus of data, you just wait until all the nodes are returning. But that's another point of the optimization, that you can concatenate the monoids while the query is running. Yes, please?
What are your restrictions in terms of computation? So what type of processing you can do in this what type of
here you can basically do any type of aggregation at all, like anything you can imagine, on the data that you can partition, well, which has a monotonically incrementing primary key. So whenever you can partition things and, well, kind of aggregate them in parallel, you can use that approach.
Assuming that semantically every data point for you should be the same as the other.
I would say so, yes. We mostly work with the time series, which is entirely homogeneous data. Whenever we get the data from one sensor, we just know that it is not only homogeneous in terms of the data type, it's also homogeneous in terms of the data meaning. So it's actually the value that's being emitted by the certain sensor.
An example, so sorry if it's silly for you. If I want to count the number of the number of pairs of 0 that are after each other, and my data is only 0 and 1. So my sensor only gives me 0 and 1.
Yes.
And I want to count all the pairs of zeros, or all the chunks of zeros that are continuous. Partitioning can break this, no?
Yes, partitioning would break that.
You cannot do then everything. This is an aggregation.
Yeah, well, but that's also kind of an a property of your data that, so basically, whenever you cannot say that things which are going to be aggregated at once and going to be yielded and transmitted to the worker node are not fulfilling the property of the monoid, which is basically keeping the structure of your data, it's going to break. So it's of course it's a limitation. Yes, the property of your data is a limitation.
I guess certain statistics cannot be performed, like probably mode cannot be performed.
What couldn't be performed?
Mode, what is the most frequent number, let's say in case of 0 and 1?
No, it could be very well performed actually. We used actually the cardinality estimators for that. We were distributing the cardinality estimators, so basically like anything like hyperlog log, you put them on the nodes are processing, then you get the approximate counters, like you merge them together, and then you can get the approximate amount, well, basically the cardinality of the data from the merged data structure. But it's kind of like reduced to an approximation. If you'd like to do just counters, you can do. So basically the count would be the grouping by the key that you'd like to have. Okay, do we have a whiteboard here?
It's fine.
So basically, you have for instance, you're counting strings. In this case, that you take the string as a key, and the value is going to be how many times it has been, it's okay, sorry about that, how many times it's been processed. And the map is actually very monoidal. Whenever you have two maps, you basically take the value of the first counter, take the value of the second counter, leave the string the same, and concatenate, well, summarize the counters. Actually, that's like if you implement the map in a particular way, or at least if you take, for instance, Haskell implementation, it would be a monoid by default. So you would basically be able to concatenate them with some merge operation just by default. Or like in languages like Java, it's going to be much more complicated. So I would say that this is the problem you can solve.
Sorry, another question that was coming to my mind is that when you were talking about this median of medians thing, that you then the array that you have to fold, where you take actually the median of medians, can become arbitrarily large.
Yeah.
As it grows. Is it a theoretical question, or do you?
That was rather a theoretical question. Actually, we never done it. What we did though is, for instance, histograms. There is actually a really nice paper written by two people from University of Israel, which is basically the streaming histogram. You just define the amount of bins you'd like to have, and you can run the streaming histograms on all the nodes, then you get them and you combine them together. It's also kind of, it fulfills the monoidal property. But of course, with mean, it's actually simpler because there are algebraic ways of reducing the mean to, some numbers that you could infer. I'm not sure. I had some, information on that, but it's not on top of my mind.
It's too much theoretical, but the thing is that when you, let's say, take mean of two arrays and combine them, both of them have the same length, and then take the mean again, then the mean would be valid. But if you take the median in the same way, and you
it won't work, yeah.
Infer in the further calculation, then you are breaking the assumption that your original input arrays was of the same length.
Yeah, in that case it works.
Yeah. That is why your input array will get arbitrarily large over time.
Yeah, that's true. So basically you would have to gather entire set of the data and then transfer it to the coordinator node and then have a large chunk or large sorted array. But once again, if it is already optimized in many ways, because for instance you could use the merge sort, which would also let you sort the data faster than pretty much anything else. And whenever you have concatenate the many things, you just pretty much
maybe you can do the same operations on your coordinator array as well.
You would be
break them into equal size chunks and then compute the stat over that again.
Yeah, you could.
Yeah.
That's true.
And then the assumption won't.
Yeah, but for that particular example, I would probably not distribute the payloads across the cluster of machines. I would actually stay on a single machine. So I would avoid transferring the intermediate results to the coordinator, and I would just perform in the memory. So that would probably help it a lot. Yes?
So normally when you work with algebras, you actually like a lot having both associativity and commutativity.
Yes.
So can you explain how you can relax on not needing commutativity? Because it seems to me that your computation framework needs to take care of preserving the order of the data.
Preserving the order, but why cannot, whenever you yield a result, you could keep it ordered in the way you could pick up where you left and pretty much continue from there. Why could not you? I don't really understand. So of course you there are cases when you would like to preserve an order, and there are cases when, for instance, you would like to get just a distribution of the data. In that particular case, you don't care about the order of your data. So you're just interested about the numbers which are coming, and you care about the curve, but you don't really care whether the items were coming in a particular order, because you would get the same thing in the end. So I would say that it very much depends on your operation. Like I cannot really come up with the. I mean, if you divide the numbers, like first divided by second, divided by third, divided by fourth, and so forth, you would, of course, in order to get a reliable computational result, you would like to keep them in a particular order. Although that's not something that you do very often with the data. Majority of the operations, in my experience, are actually commutative.
Yeah, but what I mean is when you say, okay, I rely on the algebraic structure of the monoid, I don't have commutativity, so the operators that can be in there might not be commutative, like list concatenation without sorting. So.
Yeah, well, once again, you have two different algebras. One algebra is a list, and the second algebra is a sorted list. And the concatenation of the lists is going to be like just, well, pretty much putting two things together. Concatenating two sorted lists would be, well, merge sort and so forth. So, of course, you have to implement the algebras yourself and inject them into your data. Therefore, you kind of like have the framework for that. Yes, please?
Out of curiosity, not to dig into your methods, but
no, actually this is...
Yeah, since you're collecting sensor data as well as what I said, I was wondering this notion of finding sequences of data with a certain characteristic can come up quite, at least reasonably frequently enough. So for example, I may want to see if 3 times the sensor is giving me failing data, I need to be notified. And if I'm partitioning this, I may miss these points. You know? So just to make sure that I understand, so the sort of capabilities that this partitioning and aggregation can give me, and the sort of things that it can. So in the back of my head, there is a type of problem we can maybe discuss offline. I want to understand whenever I'm looking for a pattern that spans over my data points.
Okay.
Your partitioning may break my capability of detecting such patterns.
Definitely. It will definitely break it. Once again, I'm talking more about the aggregations that are looking into the shape of the data rather than on the particular order of the data in that particular case. But from what the problem that you're describing, at least we also have that problem, although we solve it in a completely different way. We solve it actually on, well, the stream, so not on the like fused stream, but on the regular like kind of stream. So we basically, well, keep the window of the data, and then we kind of control the way so we, for instance, can say that, okay, we have collected enough the data for the window, and we can drop it, or well, stream it down to the further steps, or well, you can keep collecting the data. So I would say that the problem, especially with the sensoric data, if you'd like to detect an anomaly on the sensoric data, the most reasonable way would be to keep, for instance, the sliding window of the last, well, n data points, and then you kind of like drop the ones that well, kind of make you memory bound, so you up to your upper barrier, until you cannot collect the things anymore, and after that, like, you start dropping things. But other than that, you just keep the window of the data that is interesting for you, and you run the further aggregations on it. So I would say it's like, especially if you'd like to, so like basically what you want to do is take a window and start looking like that through your data and look whether it matches the pattern you'd like to detect. I would say that this is a problem that you cannot partition easily.
Have you ever looked at partitioning with overlapping?
Partitioning with overlapping? No, I haven't. obviously. I mean, otherwise I would probably be smarter answering that question. But this is...
I don't know if that's a solution. I'm just wondering.
No, that sounds like a solution, although, once again, we never solved it in that way. Because, well, once again, for instance, if we go back to the elephant in the eaten by the python, is actually like what we, or the types of problems we have to deal with. We can look back, for instance, like a couple of hours back. If we really need, we can actually dig down into the aggregates or roll-ups and, well, look even further for the pattern. But other than that, we just look a little bit behind us. And well, we never can look ahead because the data hasn't come yet. So these are the sorts of problems we're dealing with currently. Yeah.
Is this also, in my humble opinion, could be some theoretical limitations of the streaming analytics? You cannot do every type of analytical operation on a streaming data set, but you can do on a large data set. So it cannot deliver you every aggregation that you want.
Mm-hmm.
But streaming data set at any point is a large data set.
Yeah, but for example, if you look at the median of median examples that he pushed, if there was this assumption that the input data sets are equally large, but if you have a data set where you get 1 point at every time step, then you cannot compute this median at this particular time. You have to wait for this log to get complete so that your median of median is actually true median of the data. So these kind of things, you know, there are some theoretical limitations of what you can do with in the streaming style.
But the aggregation is always done on a finite data set. Even though you have streaming data, all you know for certain is that you might have new data later, but you're redoing the same aggregation.
There is a hidden practical pragmatically. Because that was my first response, saying exactly as you said. So you're always looking at a data set. So if you're willing to do your aggregation on everything,
the streaming algorithms assume that there is a certain amount of time before which you need to answer your query. Because then the new data set will arrive and you have the same query again. The new point in the data set will arrive and you have to answer the same query again. So theoretically, if you cannot do it in this in a bounded time set, you cannot then do it. So these kind of things apply.
Okay. Any questions?
Of course.
So probably it's a better idea to chat after the official time, just to have a group of interest. Right? Okay, so we have still some takeaways.
All the questions were good. I'm so sorry about that. I so forgot about it.
The official part is over, so we are trying to set up this meetup every month. The next will be probably December, but we will see if we found some interesting talks. And as I said already, please talk to us, give us the stuff to present, and come to us and present the interesting experience that you gain in your projects. Okay. So thank you very much for coming, and we have some beer and some water. Grab them all, and I hope you still have a great evening.
Yeah.